Good morning, and we're happy to have you today with our basic primary secondary seminar. And this is a basic building block of all hydronics. And as you will see as we go through this, it's a fundamental building block you need to know in order to work with hydronic systems. And it's a place to kind of get you started, to kind of get you a little high-level idea of what we're talking about. Here's a basic primary secondary system for chilled water. You could take the chillers and you could change them to boilers, and you got the same comments. Boilers and chillers, any major equipment, primary secondary is a tool you just have to know if you're going to be involved in this business and kind of understand it. Taking a quick look at this little setup, you see a couple of chillers, and you see a little green piece of pipe that we're going to call the common, and you see a secondary pump with a variable speed drive on it pumping out through the system. Pretty typical application. And we don't want to start there. We want to start with things real simple, but just kind of give you an idea of what it looks like at a big high level. And towards the end of the seminar, we'll come back to some slides like this and work your way through them. Another variation of this that you're seeing today is variable primary pumping. And all they've done here is eliminated the secondary pump. But that green piece of pipe is still here. The bridge of the common pipe is still here. We just put all the horsepower into the primary pumps. What we call this variable primary pumping could again be applied to chillers or boilers, any kind of equipment. And we're going to come back to this a little bit later on too. I just kind of want to get you thinking systems and thinking primary, secondary, so you can kind of dig into it. So let's go back to the very beginning now that you see as a basic building block that you've got to learn how to use. Why is that the case? Well, here's a typical large chilled water system. Could be a university or hospital or large institution. This is actually primary, secondary, tertiary. And if you take a look, you see common pipes in the chillers, and you'll see a common pipe at each individual building. And again, primary, secondary theory, that little basic building block you have to understand to be able to deal with these systems from a standpoint of balance installation and understanding how they work. So let's kind of go back to the very, very beginning of all this. What is primary, secondary? What is the theory? How does it work? And how can we take it and build up on this to get to the point that we're looking at large systems? Place to start. I kind of like calling this the good Lord's T-law. What goes in a T has to come out. And when I put two T's together, I have the common pipe and a primary secondary setup. So let's just go down to the individual T. Let's keep this real simple. This is not a complex theory. If you just go down and look at the T-law and work your way through it, it becomes pretty simple. So the T-law says very simple. If I put 150 GPM into that T, and to the right-hand side I take out 100 GPM, there can only be 50 GPM left going up, going north. That's the only thing it could be. And so the T-law says what goes into T has to come out. So kind of keep that theory in mind, and as you approach each T in the primary secondary piping, it becomes pretty simple. So let's just take that a little bit further so you kind of understand it. What I've done now is put two T's together. I've added a pump and I've added a cooling coil. Could be a heating coil, doesn't matter. But flow-wise, I want you to understand what's happening around that common pipe and that T. And we got to start with a setup like this that makes sense. So first of all, I've got 100 GPM going to the first T. I have a balancing valve or circuit setter in that common pipe closed, totally closed. And if it's totally closed, obviously the flow rate through the common pipe has to be 0. Okay, now you go to the secondary pipe, which we haven't quite defined yet, but we're defining it as we go. The secondary loop through the cooling coil, that flow rate has to be 100 GPM. So the primary flow rate's 100 because the bypass, the common pipe, has a closed balancing valve in it, and we've got 100 GPM now going through the cooling coil. I think that makes pretty good sense, and should be pretty simple. Now, what happens as we open up that balancing valve? What happens in that little piece of common pipe as we start opening the valve up? So let's take a look. If I open it up a little bit and allow 35 GPM to go through the circuit setter in that common pipe between the two T's. Remember the good Lord's T-laws. I got two T's there. What goes in that first T has to come out. What goes in the second T has to come out. So if you keep that in mind, it's pretty simple. I now have a partially open bypass. I only have a pump in my primary. There is no pump in the secondary, but I've got pressure drop between the two T's. But I'm allowing 35 GPM to go through from T1 to T2 through the balancing valve. So if you look at the first T, I got 100 GPM. I got 35 GPM going through the T. That leaves 65 GPM going through the cooling coil. So when you put those numbers up there, it's pretty simple to see what happens. Now, as I continue to open the balancing valve, as I continue to decrease the pressure drop between the two T's. That's all I'm doing. I'm decreasing the pressure drop as I open the balancing valve. Now I've jumped up from 35 to 70 GPM. Going through that T. Remember, there is no secondary pump at this point in time. The pressure drop through the T is controlling the flow rate through the cooling coil. The pressure drop between the two T's in that common pipe is controlling the flow in the secondary loop. So in this case, we allow 70 GPM to flow from the first T to the second T. I got 100 going in. That leaves 30 GPM going through my cooling coil. Coming out of the cooling coil, I got 30 GPM going back in with the 70 GPM, giving me 100 GPM leaving. Now, what would happen if I took that balancing valve or that circuit setter totally out of that piece of common pipe? And now I have removed it. I've taken it totally out. Now, here's all the theory there is to primary secondary. If there's no pressure drop in that piece of common pipe between those two T's, there'll be no flow in the secondary circuit. Hang on a second. Let me repeat that. So now I've removed all pressure drop. I do not have a pump in the secondary circuit yet. I'm going to put one in a few minutes, but I do not have a pump on the secondary circuit. And between the two T's, there's no pressure drop. 100 GPM goes to the first T, travels straight through that common pipe to the second T, is 100 GPM, leaving zero flow to the cooling coil, zero flow to the secondary circuit. I have decoupled the primary loop from the secondary loop because there's no pressure drop between the T's. That's all the theory there is. The pressure drop between the T's determines the flow through the cooling coil in the secondary circuit. If there is no pressure drop in the common pipe, there will be no flow in that secondary pipe unless I had a pump. That's what primary secondary is all about. Just that simple. Now we're going to take it a little bit further to make sure you fully get the idea. And I guess reverse of that would be, this is the same slide, I'm just going to make the same statement a little bit different. When the two piping circuits interconnected, flow in one will not cause flow in the other. When the two circuits are shown here and there's no pressure drop between the two T's, flow rate in the secondary circuit or flow rate in the primary circuit will not cause any flow in the other one. That's the same thing said a little bit different, but it's important you grasp. This is a theory. That's all there is. And the key is understanding the pressure drop between the two T's in the common pipe controls the flow in each. And if there's no pressure drop in the common pipe, then the flow in one circuit will not impact flow in the other circuit. And that's the key fundamental building block we need to get hold of. So as we work our way through this, we're going to repeat that a little bit to make sure you understand. And we're going to go ahead and give you some definitions. Now, first of all, I'm showing a primary-secondary connection with no pumps. I got primary piping. ASHRAE refers to that as production piping. Then I got the common pipe. The common pipe is between those two T's, two good old T-laws we talked about. Some people call that a decoupler. Some people call that a neutral bridge. Bell and Gossett, who came up with primary secondary, a guy named Gil Carson, defined that as the common pipe. Now, what we're trying to do in true primary secondary design is keep that pressure drop as close to zero as you can get. It could be 18 inches or some small amount of numbers, but we want it to be as minimum or as close to zero pressure drop between the two T's as we can get there. Then you see the secondary loop, the distribution pipe on the secondary loop, the secondary load side. Chilled or hot water, doesn't matter. Those are the definitions of what you need to be looking at primary secondary. And we're going to add some pumps to this and go through what we just taught you, because this is all the theory you need to understand, but we want to make sure we keep it simple and you got it in your mind. So here we go. I've got primary secondary set up now, and I have a primary pump. And it's a 100 GPM pump. I've got my little green common pipe there with no pressure drop, no circuit setter, no pressure drop. I got a secondary loop with a cooling coil, no pump. So if I flow 100 GPM through that primary loop, the first T gets 100 GPM, and it's no pressure drop in the common pipe. So 100 GPM flows through the common pipe to the second T, and 100 GPM goes on out. So there's no flow in that secondary circuit. The only way to get flow in that secondary circuit, add a pump. So the secondary pump establishes the secondary flow rate. So here we go. We add the pump we talked about. And now we have probably the first time you've actually seen the total simple little circuit of primary, secondary. Primary pump, 100 GPM. Secondary circuit in this case is 150 GPM. But now we have a primary secondary setup, and you got the definitions involved. So let's have a little fun here. If I've got 100 GPM in the primary loop, I'm showing a pump in the secondary loop taking out 150 GPM. Is that possible? Absolutely. There's no reason it couldn't be. So I've got 150 GPM in the cooling coil circuit, or the secondary circuit, and 100 GPM in the primary circuit. How is that possible? Ask yourself the good Lord's T-law. What will be the flow in the common pipe, and in what direction? And I hope you came up with a very simple answer, 50 GPM. Reverse flow. Maybe I should make sure you hear that one again. 50 GPM in reverse flow. You may not want this, but this is what's going to happen because there's no pressure drop in the common pipe. So now you see how the good Lord's T-law is working for you. That first T, you got 100 GPM in it from the primary, 50 GPM from the common, 150 GPM going to the secondary circuit of the cooling coil. Coming out of the cooling coil, you got 150 GPM. You got 100 GPM going back to the system, and 50 GPM reverse flow going back to the loop. Now, what happens to the secondary pump is sized based on secondary pressure drop only. Notice the secondary pump head loss is secondary loop pressure drop only. Make sure you don't lose that. The head loss, that 150 GPM pump, is only the pressure drop in the cooling coil circuit and the piping to the common pipe and back. You don't put any of the pressure drop in the primary loop pump. You only put in the secondary pump, the 150 GPM pump, you only put the pressure drop associated in that one loop. Now, if we start playing around a little bit with the flow rates, you should get comfortable with what's going to happen here. The secondary flow rate is independent of the primary flow rate. Now, we, in the previous slide, had 100 GPM in the primary loop. We had 150 GPM in the secondary loop. Now we've increased the primary pump flow rate to 200 GPM. But look what happened to the secondary flow rate. Nothing. It stays 150. Nothing's happened. It's still the same flow rate. But what happened in the common? Look at the common pipe. What happened there? Well, let's see. We put 200 GPM to the first T and take 150 out. That means we got to have 50 GPM flowing to the right now. So we got 50 going into the right where before it was going to the left. Now, just summarize your numbers. We go to the secondary circuit at 150. We add the 50 to it. We got 200 GPM leaving. So you see how the good Lord's T-law works if you just take your time. Keep it simple and just work your way through each T. It's not that difficult. But notice the change in the primary flow rate had no impact on the flow rate in the secondary circuit because we have no pressure drop between the two T's. No pressure drop in the common pipe. Now what happens with the secondary flow rate is independent of primary flow rate. We just said that, so let's go to the other extreme. We still have 150 GPM in our secondary flow. We haven't changed it. But look at your primary flow. We reduced it from 200 down to 50 GPM. Can we do that? Sure we can. But what happens now? What happens now? Well, we got 50 GPM in the primary, 150 in the secondary, so we didn't change the flow rate in the secondary by doing this. But what happened in the common pipe? We got 100 GPM of reverse flow now, going back the other way. So now you've been through all the examples of the good Lord's T-law. What goes in a T has to come out. And if you keep that pressure drop in the common pipe down to 0 or nothing, has no impact on the flow rate of the secondary totally. What changes is the direction and the amount of flow in the common. The direction and the amount of flow in that common pipe. We're going to use this basic little building block to explain things to you because you cannot do a modern hydronic chill water or hot water system or even plumbing for that matter, without understanding this basic concept of primary secondary. So here's a summary of what you just went through. You see your primary secondary loops. You see your little common pipe, the green. We're assuming no pressure drop in there. So what is the flow direction in the common pipe? If the primary flow rate is higher than the secondary flow rate, then the flow is going to be left to right, as the arrow shows. If the primary flow rate is less than the secondary flow rate, then you're going to have what I call reverse flow in the common pipe, or the flow, as your arrow shows, from right to left. If the primary flow rate was exactly equal to the secondary flow rate, you'd have zero flow. That happens very seldom, but it's quite possible if the two are same. So now you know all the theory on primary, secondary, and you know all the flow rates and how to connect them. Go back. Don't let these big systems scare you. Go back and look at each individual T, make you some notes, and build it out. It's real simple to follow. So let's look a little bit at temperatures of these T's we talked about, because obviously if we have different flow rates, we're mixing flow and we're mixing temperature. So here's a simple little form. We get it in front of you real quick. It's not complicated at all. But if you know the flow rates in the T's and you know the temperature, it's very easy to calculate the temperature leaving. And this is probably the thing you need to spend a little time on, because hot water with boilers or chill water with chillers, you need to understand these blended temperatures and what happens. So real simple, if I got 100 GPM of 40-degree water mixing with 50 GPM of 55-degree water, I got a total flow rate of what? 150 GPM leaving. So the question is, what will be the temperature? And if you do the math here, you see that with the little formula, it's a very basic formula, and I'm not going to spend a lot of time on it. You can play with this a little bit later when we're not so pressed for time. The temperature would become 45 degrees. But you need to get comfortable making that little calculation and being able to do it. I always tell everybody, if you know the flow rates to each T, go and put a thermometer there. Keep it simple. Then you can really have a little fun, and you can really figure out what's going on with the system if you've got a thermometer at each one of these places and you know the flow rates. So let's go to a typical little cooling coil load. It could be a heating load, don't matter, but let's just use a cooling coil for the time being. Let's add some temperatures to our cooling coils. Let's see what the impact is of changing flow rates in the primary and the secondary to the actual temperatures we see. Remember, most cooling coils are going to be picked probably on a 45-degree supply. Or you could pick them on 42 or 40 or 48, whatever you want to. But on average number is going to be around 45 because of humidification. If you try to dehumidify the air, you've got to get the water cold enough to start getting moisture out of the air. So 44, 45, let's just take 45 as a pretty common number. So this cooling coil has been designed on 45 degrees. So here we go. I got a primary supply rate of 45 degrees at 120 GPM. If I take it to my first T, good old T law, if I take 120 GPM out, that leaves no flow in the green common pipe. And the 120 GPM going at my cooling coil is at what water temperature? 45 degrees. If I got a full load, I'll come out at 55 degrees. On the return, I've got 120 GPM, 55-degree water going into the second T, mixing with 0 GPM of 45, and I got 120 GPM leaving of 55-degree water. I got a full 10-degree load on this building, and I'm seeing a full 10-degree 45 primary supply and a 55-degree return going back to my chillers. So you kind of see how that works when the flow rates are the same. Now, what happens if I start changing my own flow rates? That's the question. What would happen if I did not balance the secondary? Now, you see I jumped the secondary up from 120 to 180 GPM because you didn't balance. You didn't have a circuit set. You didn't balance. And balancing is critical. Here's one example of why balancing is so important. And let's just take a quick look. So the secondary circuit has not been balanced. It's flowing 180 GPM. Design was 120 and a 10-degree delta T. Now the BTUs are not going to change, but we've increased from 120 GPM to 180, so the delta T's got to go down. Let's just check this all out. So first of all, let's get all your numbers up here so you see. What I want to ask you is what impact will overflowing the secondary circuit have on the supply chill water temperature? what impact will not balancing and have an overflowing on the secondary chill water loop have to the supply chill water temperature to that cooling coil? And what is that going to do to dehumidification? What's that going to do to you in maintaining conditions in your space? Think about it. Okay, primary supply chill water is 45 degrees. I got a flow rate of 120 GPM to that first heat. I take out 180. Yes, I can take 180 out if I have reverse flow of 60 GPM coming from right to left. So here we go. I've got to have a 60 GPM coming from that side. Now the question to you is, what kind of water is that? That's hot return water. We got hot 55-degree return water, 60 GPM, mixing with 120 GPM, 45-degree water. They gave me 180 GPM of what? What temperature would my 180 GPM be? You got to balance it. Roughly 48 degrees. A little less, but roughly 48 degrees. So now what have I got? I got a secondary circuit with 48 degree supply water. The design for my cooling coil was 45. It is not going to dehumidify. It's not going to cool properly. You got plenty of water, but it's not cold enough. You're giving your cooling coil 48 and you picked it for 45. It's not going to work. Return is 55. What's wrong? You didn't balance. You didn't balance. Everybody see that? Everybody got the numbers? How would you fix this? How would you go about fixing this problem? Well, there's a couple ways you could fix it. Two ways, really. You can change the flow rate to get a coil supply temperature down to 45 degrees. How would you go about fixing this to make sure your cooling coil got 45 degrees? I hope you would consider decreasing the secondary flow rate by putting a balancing valve or circuit setter on it and balance it to 120. Because if you do decrease the secondary flow rate to 120, you will reduce the chill water supply temperature to 45 degrees. Unfortunately, what a lot of people might say is, I don't have enough 45, and they're going to increase the primary. When you do that, you got a mess. So I should take a quick look and make sure you got the numbers. If I did it the right way, and that is balance, and take the secondary loop back to 120, I got my 45, 55, everything is balanced, 120 coming in at 45 degrees, nothing in the common pipe, taking 120 out at 45, return is 55, 120 GPM at T number 2, nothing in the common pipe, 120, 55, everything's a perfect world. Great. Let's do it the other way. Let's increase the primary supply to 240 GPM. You know, common sense would tell you, I don't have enough 45-degree water, let's get more 45. And that's true, you can fix it that way. So in this case, the guy decided that, okay, I'm going to make sure I got plenty of 45-degree water to my cooling coil, so I'm going to raise it to 240 GPM. I know that'll be enough. It will work. Sure to work. Now I've got 240 GPM going in. I did not balance the secondary loop. I left it at 180. Remember, the design flow for the secondary was 120, but I left it at 180 because I didn't balance. But by increasing the primary flow rate up to 240, can I take 180 out at 45 and get my chill water temperature back down to 45? Absolutely. So now I got 180, 45 going to the cooling coil, but look at your return temperature. Your return of 180 GPM out of the cooling coil is now 52. Design was 55. BTUs don't change. Q's equal GPM plus 500 times delta T. So my delta T now is 7 degrees because my flow rate's up to 180 GPM. So now I got 180 GPM of 52-degree water mixing with 60 GPM of 45. It gave me 240 GPM back to my chillers that were designed for 10-degree delta T, have an elevated and a reduced temperature, approximately 50 degrees. So now I've got 5 degrees across the loop. How's your chiller going to load up? We'll talk about that in a minute, but the answer is it will not. This is problems. So here's your basic formula we kind of went through. I think everybody understands it. If not, take your time to learn it. And let's apply it to a typical primary secondary setup so you start pulling some of these pieces together. And don't worry, we're going to get them all together at a high level, but I want to make sure you got this fundamental building block of primary, secondary in your brain and real happy with it. So here we go. I got a crossover bridge here. Again, it could be hot water, chill water. In this case, I'm using chill water. Got a crossover primary bridge at 40 degrees. I hope to go back to my chiller plant at 55. I'm taking out the 750,000 BTUs. I got a delta T of 10 degrees on the secondary side. So using that Q is equal to GPM times 500 times delta T formula, what are my flow rates to each set of pumps, and what would be the delta T. And I hope when you do the Q, 750,000, and you do the delta T on the secondary loop of 10 degrees and solve, you come up with 150 GPM. On the primary loop, your Q is still the same. You know, energy in's got to be energy out. So on the primary loop, it's still 750,000 BTUs, but I'm using a 15-degree delta T. So I've reduced my flow rate to 100 GPM. It's 50% less than the other one. So you kind of see how this works with the delta T and the GPM and the BTUs. That's why you need to get in your mind the heat transfer is the same through both sides. And now we have the ability with the primary secondary loop to have different flow rates on the coils than we do in the distribution piping. That's a pretty neat idea. And we're going to take that as we go a little bit further to show you some typical good applications of primary secondary. So now you see the total set of numbers on that, and let's keep going a little bit further. How could primary secondary help you reduce piping sizes? We're going to use that same example we just showed you where we mixed delta T's. We had a primary delta T of 15 and a secondary delta T of 10. Here's a setup with a 10-degree chiller, 45, 55, 150 GPM. I want 45, 55 on my coil. I want 150 GPM on my cooling coil. But I'm going to size my pipe, 4-inch pipe. And who knows how long that pipe is? It might be 500 feet of 4-inch pipe. I do not know. So we're going to take primary, secondary, and apply it to this piping situation to see if we could save you some piping costs. I'm not going to look at chiller operating costs right now. I'm just going to look at chiller. I'm going to just look at chill water piping costs. First cost of the pipe size. I got a 4-inch pipe. Could I reduce that to 3-inch? Sure it could. How would I do that? I go to primary, secondary. In fact, this is the same setup as the previous set of slides. Now I have changed the delta T on my primary loop to 15 degrees, where before it was 10. Same BTUs. So now I'm flowing 100 GPM through my primary pipe. I can reduce the size to 4-inch down to 3. I reduce the first cost of the insulation. I reduce the first cost of the pipe, the labor, from 4-inch down to 3. Is that important? If you got a long run of pipe, it might be. If it's a short run of pipe, it may not matter. You're going to have to set your chillers up to make 40-degree water with a return of 55. Now let's go to the secondary loop. Let's go to that bridge down there. We still want my cooling coil to see 10-degree delta T. We still want 150 GPM on my cooling coil. How does that work out? We'll take a quick look. I'll put a bridge. Sure enough, I'm going to have reverse flow in my common pipe. I'm going to have 50 GPM reverse flow in my common pipe. My 55-degree water, 50 GPM is going to mix with 100 GPM of 40-degree water to give me 150 GPM of 45-degree water going to my cooling coil and 55 back out. So what have I done? I've decoupled it, and I've reduced the pipe size, and I've also reduced the operating cost. There's my 3-inch pipe size. Let's look at pumping costs. So get all your numbers up here real quick so we can talk about it. Just one more quick slide. Here we go. So now we got primary, secondary, and lower pumping costs. With a 4-inch pipe, I was doing 150 GPM to flow through the whole system, all the pipe. And at 40 foot ahead, 80% efficiency, get the same set of numbers, it takes 1.9 brake horsepower. Now by adding a secondary pump, I've added a pump. I got a primary pump now and a secondary pump, but my primary pump now is pumping 100 GPM. The 25 feet ahead is just a head required to get it to the common pipe. See, the head now for the primary circuit does not include the cooling coil at the bottom. Primary, secondary is just that primary loop is only 25 feet ahead. There's a secondary loop for the secondary pump for the other 15 feet ahead. And notice the total head stays the same. You got 25 feet ahead in the primary loop, 15 feet in the secondary loop, but the flow rates are different because we used a 15-degree delta T. On the primary loop, we had 100 GPM. On the secondary loop, we went back to 150. But when you add it all together, even with 2 pumps, you only have 1.5 brake horsepower versus 1.9. So you can reduce the operating costs when you understand this concept. We're going to take it a step further. Let's take it a step further with a primary, secondary, pretty typical application, especially if you've got a primary pump going on, you've got multiple buildings, a campus type thing. Let's just see how you might take this newfound knowledge of yours, a real simple application here, and see how you might reduce pumping operating costs. Pump operating costs should be something we should all be concerned with. So look at your circuit. You've got a primary pump. You've got 5 feet ahead in each segment. And the thing you should pick up on pretty quick is that look at circuit number 3. 1,000 GPM, 40 feet. One circuit, 1,000 feet, 40. The second circuit, but circuit number 3 jumps to 100 feet ahead. Not 40, 100. The flow rate's only 500 GPM, but it's 100 feet ahead. The last circuit out is back to 40 again. So if you had to pick the pump head for that pump, which would be the path of most resistance? Where is your path that you got to pick your pump head for? We know the total flow rate's got to be what? 1,000 plus 1,000 plus 5 plus 5. It's got to be 3,000 GPM. We know the total flow rate has to be 3,000 GPM. But what pump head do we have to pick the pump for? And I hope you recognize it's going to be that zone 3. And it's going to total up to 5, 5, 15, 30, 130 feet ahead. Everybody see that? 5, 5, 5, 100 feet ahead for the zone and 15 feet getting back. If I pump that circuit at 3,000 GPM, do I have enough head for all the other circuits? Absolutely. It's a piece of cake. We've got plenty. But that's the circuit controlling the head on 3,000 GPM of flow, not 500. And that's the key to understanding what primary and secondary might do for you here. So let's take a quick look at this. If I do a 3,000 GPM, 130 feet ahead, keep a very efficient pump at 80%, I'm 123 brake horsepower. At 6 cents a kilowatt hour, I'm at $4,800 a month. That's a lot of dollars, all tied to primary, secondary we have not used it, all tied to the high head zone. Now, could we apply primary, secondary here and break off those high head zones and maybe reduce the operating cost per month? Remember the 123 brake horsepower. Remember that. Let's take a look and see what we might do here. Look at the circuit settings, by the way, when we do the balance on this. This is a direct return system. I balanced each one. Look at the pressure drop in the first circuit, 80 feet. Man, that's just wasted energy. Look at the second circuit, 70 feet. That's just wasted energy. Look at number 4, 50 feet. That's just wasted energy. All because circuit number 3, that circuit set is open. All because of that 100-foot high head circuit that we could isolate with primary, secondary. Wow, now we get something to work with. Let's take a look. What have I done? I added pumps. I still got my 3,000 GPM pump 1, but I'm going to use primary, secondary on zone 3 and on zone 4. And I'm going to have a primary, secondary pump P2, the secondary pump P3, and I'm going to take off that 500 GPM 100 feet ahead. I'm going to take it off pump P1. And I'm going to go ahead and take it off pump P3 because I need to do that too because you punch it out. It makes sense there. It's kind of a hybrid system. Notice we don't have primary, secondary in every building or every zone. We only have it on zone 3 and zone 4. Zones 1 and 2 are being pumped by the primary pump, which is fine. People don't seem to understand it's okay to mix this. It's okay to take one circuit and make it primary, secondary. You don't have to do all of them. That's one of the biggest mistakes we make. And we'll talk about hybrids a little bit further. Let's see what we've done now to the pump operating cost. All right, here we go. So now where is the highest head drop for a primary pump? It's no longer zone 3 because we took the 100 feet ahead off. It's no longer zone 3. It's no longer zone 4. The highest head loss now is zone 2 for the primary pump. Remember it was 3,000 GPM at 130 feet ahead before when we end that primary pumping situation. Now what is it? Now the highest head is what? 5, 10, 15, 20 plus 40, 60 feet ahead. I only need 3,000 GPM at 60 feet ahead to flow that. Now if I flow 3,000 GPM with 60 feet ahead, is that enough head to flow to the common pipe of zone 3 and the common pipe of zone 4? Absolutely. We got plenty of head there to flow it down to zone 3 and 4, and we're going to take up there with a secondary pump, and we're going to see what happens. So let's total back up the total brake horsepower for our 3 pumps. Remember before, I think it was 139, I believe, but let's just go see what we got. Pump 1 now is 57 horsepower, so we got to add 2 more. So pump 2 was 500 GPM at 100 feet ahead. Same efficiency, 80 playing no games here. I got 16 brake horsepower on pump 2. How about pump 3? Pump 3, same efficiency, 80%. I need another 6 brake horsepower. When I total it all up, and let me go ahead and total it up for you. I get a total of 79 brake horsepower required. Before, I believe it was 139. Now I'm down to $3,100 a month, which saved you $1,500 to $1,600 a month, times 12 months. That's at 6 cents a kilowatt hour. That's a huge savings. And we're using 3 pumps versus 2. Note the pressure drop on the circuit setters now on the primary pump. Zone 1, 10 feet. Seems like before it was about 80. In zone 2, I got the number, but it's now open. The bottom line is we've taken a lot of pressure drop out of the system by using primary, secondary. This is a beautiful application. You need to learn this. This works on direct return systems, isolate your high head zones, and make all kinds of savings in pumping costs. So you kind of got the idea. It was 123. I'm sorry. I think I said 139. It was actually 123 before. Brake horsepower is now 79. I've reduced it from $4,800 a month to $3,100 a month. What a great savings by just a simple little application of your basic knowledge of primary, secondary. Now you begin to see why this is so important that you learn. We can always look at flow balance too. Here's another little item about primary, secondary that makes it very attractive. Flow balance. If I adjust the flow in any of these zones, I'm going to adjust the flow in the other zones. I think you see that. But when you got primary, secondary, I can balance zone 3 with pump 2 and zone 4 with pump 3, and they're isolated. So whatever I do in those zones has no impact on the primary flow. It makes balance in a system with building blocks. In other words, you can go to an individual piping loop and balance it. And as long as you have no pressure out in common pipe, you have no impact on what happens in the secondary circuits. So let's take a few quick ideas and some comments on a little higher level. Where would you see primary, secondary? What are some applications you might want to take a look at? Here's a typical one with primary, secondary chiller loop. And I have 3 chillers, 3 pumps, common pipe, secondary loop with variable flow. I got constant flow on the chillers, variable flow on the secondaries. Let's just take a look, a couple other quick comments, questions that come up all the time. You engineers are always asking, where is the best place to put a Roll-Atroll on primary, secondary chiller systems? It will work at many different locations, no doubt. But we believe where we got it shown here, and this is what Bell and Gossett preaches, put it on the return from the secondary loop. That's where you're going to have the hottest water and the lowest pressure, right there, because it's close to the common. Get it close to the common, come in on the hot return water, that would be the best place to put it to get the most out. So that would be an answer to that question that comes up all the time. So now going back to a primary secondary loop, we have a dedicated pump per chiller. You see the common pipe, and you see the secondary pumps going off. And we kind of play with this a little bit to see if you want to stand by, we could just add a butterfly between the 2 chillers there as shown. Now you've got either pump to either chiller. You've got a great little primary, secondary setup with a dedicated pump per chiller. The new things that are coming on, obviously, are some people like to pinch leg them together with parallel pumps as shown. It's still primary, secondary. You see the green common pipe. You got secondary pumps. But if you've got a pipe in this way and they're not dedicated pumps in a primary, secondary loop, you need to put 2-way isolation valves on each chiller as shown and flow limiters on each chiller just to protect them. And that's another old seminar we can dig into deeper, but I'm just cautioning you, if you want to pipe them this way, great. Just make sure you have the 2-way isolation valves and you have the flow limiter. So let's put a little notes on the common pipe from B&G. People always asking the questions, how long does a common pipe needs to be? What is the max pressure drop in a common pipe? And B&G's answer is, in theory, none, but everybody wants a real number. Let's give you a real number. B&G is going to say, try to keep your max pressure drop not to exceed 1.5 feet or 18 inches. 1.5 feet, 18 inches. Very easy to do if you put 2 T's and keep it close together. They also like to make sure that pipe size is the same pipe size or equal to the pipe size of your largest chiller. The other comment is, what is the minimum length between the 2 T's? Bell & Gossett did a lot of testing with this, put it in the lab, and trying to force flows that have a problem. And their comment came back, let's make it a minimum of 3 pipe diameters, and let's keep the pressure drop to less than a 1.5 feet. You're not going to have any problems. So there's your answer. 3 feet max, keep it a 1.5 feet pressure drop. You will not have any mixing problems. So back to my primary, secondary, chill water delta T's, low chill water syndromes. Let's look at a real world application of primary, secondary, and try to get some of this concepts into a little higher level now involving primary, secondary, what happens in a loop. I've got 2 500-ton chillers here. Let's make them 12 degrees delta T on the chill water side. I like 12 degrees because it's 2 GPM per ton. So this system could make, with the first chiller, 1,000 GPM, second chiller on the line, 2,000 GPM. Designed as 5644, constant flow to chillers 1 and chiller 2. Look at my green, common pipe, primary, secondary. I've got a secondary pump that's variable flow, 2-way valves on the coils, and that flow is going to vary. Let's see what happens as I vary the flow on the secondary loop in staging chillers and what happens. Remember, to load this chiller up, design is 44 supply, 56 degree return water, 12 degree delta T. So let's just take a look. There's 3 possibilities of what's going to happen with these chillers in the primary, secondary. Go back to your basics, remember? If the primary flow rate equals to the secondary flow, primary flow rate could be greater than the secondary flow, or the primary flow could be less to the secondary flow. What will happen to these temperatures as we do that? I think it's important you put all this information together, basically, that you've learned, and let's see what happens to the temperatures as we play with this. So let's take each one of these cases, put some numbers to it, put some temperatures to it, and let's just see where we are. I think you'll enjoy doing this. So here we go. Primary flow rate equal to the secondary. I got chiller 1 on, chiller 2 off. I got 1,000 GPM coming out of my chiller. That's at 44 degree water. If I take 1,000 GPM out to my secondary circuit, what? No flow in the common pipe. It's 0. Assume I got good coils out there. I take 44 out of 1,000 GPM. I'm going to bring 1,000 GPM back at 56 degrees. Great. I got 1,000 GPM, 56 degrees water coming back to that second T. No flow in the common pipe. So my first chiller sees a return water temperature of what? 56 degrees. So chiller 1 is fully loaded, 12 degree delta T, producing 500 tons, return is 56, supplies 44. A perfect world, fantastic world. The primary flow rate is exactly equal to the secondary flow rate, and there's no flow in the common. You won't see that very often, but that's a possibility you need to understand. So let's just keep going with this concept, and let's go with the primary flow rate greater than the secondary. I got 2 chillers online now, chiller 1, chiller 2. So I'm producing 2,000 GPM of 44 degree water. Both chillers running, 2 GPM per ton, 1,000 tons there. I can produce, and I am producing, 2,000 GPM of 44 degree water. Now, how much water are we going to take out in the secondary loop? Well, let's take out 1,500 GPM. So now we get more to a real world situation. I've taken 1,500 out. What does that mean to my common pipe? Yeah, now you see how much fun this can be. So now we've got, going south, 500 GPM in the common pipe of 44 degree water. Great. So you see how the T's have to sum up? So I take my 1,500 GPM of 44 degree water out to my system, and I bring it back 1,500 GPM at 56 degrees. And it's going to do what at the T? I'm going to have 1,500 GPM of chill water returned at 56 degrees, mixing with 500 GPM of 44 degree water to give me 2,000 GPM of 53 degree water returning. Now you see what you've learned. You see how important this is to get all this together. So each chiller now has 53 degree return water, 44 supply, 2 chillers running. Everybody's still happy. Everybody's working fine. And this is a mode the chiller's running all the time, the primary, secondary. So each chiller is 75% loaded. There's a 9 degree delta T, 53 to return, 44 supply, 9 degree delta T, and the design was 12. So I'm 9/12. So each chiller is 3/4 loaded. Typical operating condition in the system. How about if our primary flow rate is less than the secondary flow rate? Let's just take a look. What am I going to do here now? I've got 1 chiller running, 1,000 GPM, 44 degrees. Chiller number 2 is off. what happens, or can I take out 1200 GPM? Wow, interesting, huh? You telling me I'm going to take out more water than I'm putting to the T? Yeah. Now, what does that mean to you? What have you learned? What's happening in the common pipe? That means I got 200 GPM going north, bottom to the top of the screen on common pipe. And what kind of water is that going to be? Let's just see. Let's put all the numbers. I think you understand it's going to have to be hot return water. We might have a problem here. Let's just see what happens. Suppose I take the 1200 GPM, now it's going to be 46. Now I bring back 1200 GPM to 56. I'm seeing a 10-degree delta T. But here's what gets to be interesting. I'm bringing 1200 GPM back at 56. But where is the 200 GPM coming from going south to north to mix with 1000 GPM of 44? It has to be 200 GPM of 56-degree water. So I've got 1200 GPM going to the bottom T at 56. I got 1000 GPM at 56 going over to my first chiller. That leaves 200 GPM going north of hot 56-degree water, mixing with 1000 at 44 to give me 1200 GPM of 46-degree water. That may not be desirable. Your cooling cores may not work. You may have a problem here. How would you solve the problem? One thing you could do is stage on the chiller number 2. Chiller number 2 is off right now. We could turn it on. What would happen to this exact setup if I turn on the second chiller? Well, if you recognize, put the numbers up here real quick so I don't want to bore you with some of this. I've increased my 2000 GPM at 44 degrees to the first T. I'm still taking out 1200, but now I've got 2000 going to the T, so now I've got going north to south 800 GPM of 44-degree water. I'm bringing my 1200 back at 56. So I'm mixing, and I wind up with each chiller seeing 51-degree return water. In other words, I've got 1000 GPM of 44-degree water going out. I bring it back to the chillers at 51. So each chiller is seeing a delta T of what would that be? 7 degrees. I've got 2 chillers running now. Everybody's happy. I'm keeping 44-degree water to my chill water coils. Everything is fine. And the good news is I got that 56 hot return water coming back. Now, I want to play with that 56-degree return water a little bit so you can understand this term low delta T syndrome. I want you to kind of have a feeling for that. So we go back to this form, and I said 2 GPM per ton is 12 degrees. Now, if I look at my chillers and I put my GPM in a ton being 12,000 BTUs, and if I had a 500-ton chiller at 12-degree delta T, my flow rate's 1,000 GPM. So I like looking at this because 12-degree delta T on chill water is a good design. Nothing wrong with it. It's 2 GPM per ton. It's a great design. And it makes the numbers simple for what we're doing. But all we're going to do is take that formula and change the delta T. Are we going to change the flow rate? What happens to the delta T? That's the thing I want to ask you. So let's take a look at this. Here's my 500-ton chiller. You designed it for 1,000 GPM at 56-degree return and 44 supply. And as you can see with the BTU formula, 12,000 BTUs per ton, that is a 500-ton chiller. I want everybody listening to me, just sometimes I sound a little crazy when I say things, but get this in your head. This is worth you listening to. You cannot load anybody's chiller up unless you get the return chill water temperature up. If you don't give a chiller the design return water temperature, you can't get the tonnage out of it. It's impossible. So right now, I've got 56-degree water going to my chiller. I'm producing 44. I've got 500 tons. What happens if you don't give me hot 56-degree return water back? What would happen? Right now, the chiller is fully loaded. What would happen if you reduce my chill water return temperature to 54 degrees? I just did it for you. Do the math. What happens? Where do I wind up if I do that? I wind up with a 10-degree delta T versus 12. I still got 1,000 GPM. My chiller's going to give you 417 tons, not 500. Now, you bought a 500-ton chiller, and make sure you get this simple statement. This is very important. I'm repeating myself. You have to get the return chill water up to design to get max delta, to get max tonnage. In other words, if you're producing 44-degree water on this 500-ton chiller, and you never give me water back any hotter than 54 at 1,000 GPM, you're never going to get more than 417 tons out of the chiller. It's impossible. You cannot get any more. You're hung. So what are you going to do? Chiller is only 83% loaded now. You bought a 500-ton chiller, and you can't get 500 tons out of it. This is the part you need to get straight. If the chiller set point is fixed at 44, you can't do it. What are we going to do? Let's just call low system delta T. We've got that 500-ton load out there. We're producing 2,000 GPM at 44-degree water. I'm taking 1,200 GPM out. I've got 800 GPM in the common pipe. Same numbers as before, but look what I've changed. Instead of coming back at 56, I'm coming back at 54. I have low delta T syndrome. Same setup before. I've got two chillers running, 2,000 GPM, 44-degree water being produced. I'm going out at 1,200 GPM at 44 degrees. I'm coming back 1,200 GPM at 54, not 56. We cannot meet the 500-ton load with one chiller. Slow down and take a look. Do the BTUs in your mind. I know we're in a hurry as always, but load is 500 tons. I'm having to run 1,000 tons worth of chillers. I'm having to run two 500-ton chillers to give you 500 tons because you have low delta T syndrome. Design was 12-degree delta T on the load side, but you're going out at 44, coming back at 54. I only got 10 degrees. So now we got a problem. We have to run both chillers to give you 500 tons. Bottom line is, what's going to happen if you get a total 1,000-ton load? You can't get the BTUs out. So now you got 50-degree return water to each chiller, and each chiller is going to give you 50%. Look at the wasted energy because of this low system delta T. Nothing to do with primary secondary. This is because you're not giving me 56-degree water back. You're giving me 54. What does that do to you? Look at all the wasted energy going on this thing. We got to run two chillers to make 500 tons. So we double pumping the primary side. On the secondary side, instead of pumping 1,000 GPM, we're pumping 1,200. Friction goes up. I got more pressure drop. I'm having to run two chillers, two sets of pumps, two sets of cooling tower pumps, and two cooling towers. So energy-wise, low delta T, I'm not getting the 56 back. It only gives me 54. You're paying a huge penalty in the operating cost, a penalty that everybody has been published. You see all the magazines, and everybody says this is the issue. What are we going to do about it? So our chiller plant cannot give you 1,000 tons at low delta T. Remember that. If I only got 417 out of it, if I double that, I can only get about 835 out of it. In other words, I'll never get 1,000 tons out of this 1,000-ton chiller plant until you give me hot return water, till you give me my 56. If you're going to insist on giving me 54, I cannot give you 1,000 tons. That's what you got to kind of understand. So let's take a little bit of a look at this. How can we fix the problem? First thing to do is fix that low delta T problem out of the system. If you can fix it, get the 56 degrees back up, you're going to win. You're going to save energy. You're going to have plenty of chiller capacity. You're going to be able to get 1,000 tons. But get this straight. It's not a primary secondary problem. It is a system problem. It's out in the system. So the easy thing is to get that 56-degree water up and fix your problem. If not, you're going to have to buy another chiller. That seems a little crazy to me, but we see this every day. Yeah, we see this delta T syndrome every day. We see people fixing it by buying a third chiller because they don't get the return chill water temperatures up. I cannot repeat that enough. Get that idea in your mind. When you look at systems, think in terms, what should the return chill water temperature be? You got variable flow and two-way valves. It should be at design or higher. So where are we going with all this? When you look at primary, secondary systems, you need to understand the impact of varying the flow and two-way valves. You need to understand the impact of not having design return chill water temperatures. Here's a typical campus system now. We're going back to the slide we had earlier, remember? Primary, secondary at the chillers, primary, secondary at the dorms, primary, secondary at the gyms. You see how this primary, secondary concept fits all over the place. As we work our way through this, you kind of get the idea of a campus system, a central chill water system. You're going to be using block loads. You're going to be using variable flow in the distribution. The chillers themselves may or may not have variable flow. This depends on how you want to design it. But tonnage-wise, you're going to say the kids won't be in the dorms at the same time doing the gym and the basketball. They certainly won't be in the library at the same time in the dorms. So a big system, and all systems are like this. On big systems, what you want to do is have two-way valves and the ability to move the chill water around to where you need it. So you can move the tonnage from the chill water plant where you need it. So in this case, if you total up the total peak loads, trying to make an example here, you see you got 1,000 tons each block. So your total peak load is 4,000 tons. But if you run a block load, knowing the kids can only be at one place at one time, then the definition of diversity would be the block load is 3,000 tons, individual peak loads are 4,000, but the kids can only be one place at one time, so the definition of diversity is 0.75. So the message to you is, if we design this thing properly, we can buy 3,000 tons worth of chillers from a chiller plant. If you don't design it properly, you're going to need 4,000 tons or higher. If you got chill water delta T syndrome, you can't move it around properly, you've got to have that delta T to make it work. Primary, secondary gives you building blocks to work with. This is why it has become so important. So if we kind of summarize all this, and we hit you with a lot, but I think it's important you understand that you cannot design a building today without primary, secondary, certain form of fashion. And if I look at the building blocks out there that you need to understand, of which primary, secondary is a big piece of, you design a chill water system, a hot water heating system, a chill water plant, a hot water plant, central plant, you're going to be using one of these building blocks or combination thereof. Primary pumping, primary secondary pumping, primary secondary tertiary, primary secondary tertiary hybrid, and primary secondary zone. I'm not wanting you to be experts today. I just want to plant these little concepts in your mind. Here's a verbal primary pump or primary pump loop, and you see a little green pipe. You see all this going on. But you need to understand primary, secondary pumping, how this works. One set of pumps, pumping everything. Yes, you got a green pipe, but remember the common pipe and the primary, secondary theory. We remember if we put pressure drop in the common pipe, we force circulation in the secondary. That's all we're doing here. We get a little bypass, green common pipe with a valve in it deliberately that we're throttling that valve to control the flow rates through the chillers and through the system, primary pump. Here's a typical primary secondary system we looked at. We've got a dedicated pump per chiller, constant flow. Again, see the common pipe? And you got a little secondary pump with two-way valves, primary, secondary. The secondary is variable flow. The primary is constant flow, primary, secondary. Wow, here's that chiller, big chiller loop again, the big campus loop. But don't let this catch you off guard. Don't be confused by this. Remember that simple T-law. Remember the simple common pipe. Primary, secondary, tertiary. Now we got a primary chiller loop or a boiler loop, dedicated pumps per chiller or boiler, little common pipe, secondary loop, secondary pump, variable flow with two-way valves in the bridges, and each individual building has a pump and two-way valves. Primary, secondary, tertiary, and I hope you see all the common pipes on here. Every one of those common pipes tells you another application for primary, secondary. And give you a summary here, what's good and bad with this, and this is not the intent today, just kind of a handout, because this is a high-level application stuff, but primary, secondary, tertiary considerations make a lot of sense, and this is kind of walk you through that. Now here goes primary, secondary, tertiary, or hybrid. Remember the pumping example I showed you about how you would isolate the high head loss zone? That's all we're doing here. Don't make the mistake of trying to put tertiary loops on every building if you don't need it. Primary, secondary. I got primary loops, chillers, dedicated pumps, constant flow. That's a little green common pipe. I've got a secondary pump pumping zones A and B. There's plenty of head on that distribution secondary pump to pump zones A and B. Way out of the system, I've got zone C with a high head. I'm going to isolate that zone with a tertiary pump. Therefore, we call this primary, secondary, tertiary hybrid. It's got a little bit of primary, secondary in it, and it's got some tertiary loops as well. Another concept that's been around quite a while is zone pumping. And again, it's a version of primary, secondary. Notice here, we got dedicated pumps for each chiller, constant flow. We got a little common pipe for the decoupler. And instead of having one big distribution pump, we have pumps in each zone. And each zone pump is pumping its zone and the distribution piping out to it, called primary, secondary zone pumping. I'm not trying to make you an expert. I gave you some pluses and minuses with that. All I'm trying to do today is plant the concept with you that everything you look at is some version of primary, secondary. Every single thing you look at. So you got to get the common pipe down. Here's some advantages and disadvantages of each one. And again, the purpose is for you to understand you cannot do a chill water system today, you cannot do a hot water system today, you cannot do a plumbing system today without applying primary, secondary in some form or fashion. That's why it's so critical to you that you get that little basic, simple building block in your mind so you can begin to understand some of these concepts and how we got there. Ladies and gentlemen, it's been fun. We appreciate your time. Have a great day. If you have any questions, I'd be happy to answer them. Thank you very, very much for your time.